Hi everyone. Today I'm going to be talking about the environmental impacts of laptop enclosures using life cycle assessment to support sustainable consumer electronics. Objectives of this project include the introduction, the background, the life cycle assessment, the results, and the conclusions. The learning objectives for today, students will be able to explain the environmental impacts associated with the consumer electronics. And then also a question that you guys can answer is, using the LCA method, what was the main emission that was used from the production of laptops and where does this emissions arise from? Next, we're going to be talking about the background of the article chosen. So over the past 40 years, a developing and expanding number of computers, mobile devices, and other consumer electronic devices has transformed daily life in areas of communication, entertainment, and personal productivity. So it is estimated that since 1980, more than 900 million desktop computers and laptops and more than 700 million cathode ray tubes, known as CRT, and flat screen monitors have been sold in the United States. So the total market for personal computing devices is expected to continue to grow by 11% globally between 2013 and 2015, with nearly all of the growth occurring from the tablets, mobile phones, and then other ultra mobiles. So next we're going to talk about the introduction. So there's many environmental impacts associated with consumer electronics. To start off, climate change impacts include large embodied energy related to manufacturing and use to the risk of human and ecologic health effects that may result from the release of these toxic materials such as the heavy metals, the flame retardants, and etc. during an end-of-life management. So due to the increase in sales of these devices, the manufacturers, policymakers, and the purchasers are looking for ways to reduce the life cycle environmental impacts of the electronics by encouraging greener designs and then safer materials, along with increasing the reuse and the recycling of the materials chosen. The objective of this study is to perform a screening level life cycle assessment of the laptop enclosure and to provide knowledge to support the development of the more sustainable consumer electronic products. In this study, that's the main focus, was to identify that recycling needs to happen, reduce the greenhouse gases, and use greener designs in order to not cause so much emission for the products of the laptops. So to start off with the research, this article identified the environmental impact of the laptops and computers. They used a life cycle analysis to do so. Researchers are in need of finding a solution to reduce the emissions due to the increasing amount of people that are dependent on the products of these items of the laptops and computers. The main takeaway from this LCA is to compare the typical housing made from the fossil plastics with the alternative materials that I will discuss later that include the aluminum and the materials made from the renewable feedstock such as the bamboo and the polylactic acids. So on this slide, this is more of just an overview of what I'm going to be discussing. In the next upcoming slides, I'm going to discuss the goal and the scope, the life cycle inventory, the life cycle impact analysis, and also the data interpretation. So this slide, we're going to discuss the goal and the scope of the project. So the goal of this study is to evaluate the cradle-to-grave environmental impacts of a common consumer electronic device such as the laptop enclosure and where it's manufactured from, the fossil plastics, the biomaterials, and the metals, along with the combination of these to identify what aspects of these materials must be improved to promote environmental sustainability within the consumer electronic market. So the main goal of this criteria is to promote materials that meet a performance requirement but also have a smaller environmental footprint. So the scope of this is to use information found from both the product developers and the policymakers with the help of addressing emerging concerns surrounding the electronic manufacturing and the e-waste of the products. All the identified processing steps throughout the life cycle were modeled and included the upstream material feedstock production. It included the enclosure forming, the transportation, and then also the end-of-life treatment. So now getting into the life cycle inventory, we're going to talk about the raw materials that could be alternatives, such as the aluminum. I'm not going to attempt that name, but the PCABS, the polylactic acid, which is also known as a PLA, and then bamboo. And we're going to discuss the manufacturing, the distribution, / transportation, the use, and then the disposal of these raw materials. So on this next slide, this is the LCA for the aluminum material. It starts off with the primary aluminum mining. It goes into the refining and the recovery, and then you have the secondary aluminum scrap that goes into the melting phase. And from there, it then goes into the die casting or the CNC milling, and the aluminum will then be polished and finished, and then the assembly of the laptop will occur, and then the use from the consumer, the disassembly of this laptop, which will then be recycled or sent to a landfill. So this material, PCABS, this is another LCA for the material, which is the crude oil. Again, this is the same process of the LCA. There will be the assembly of the laptop and all of the processes to get there, from using the plastic material, then the use from the consumer, the disassembly of that laptop, which then will lead to the recycle and the landfill. The difference for this material is the recycle. After the recyclement, there's a few stages that filter back in. So recycling actually is a big factor for this material because of the cycle of the raw material that is used over and over. For this PLA life cycle assessment, we start with corn, which is a biomass, and then it's a lactic acid, which has a condensation, which leads to compounding, and then has arisen and leads into the laptop assembly. It has the use of the laptop again, the disassembly, and then instead of recyclement, there's two different options. There's a landfill and then the electricity production. So this is a different type of recyclement. Therefore, we're using the electricity generated. So to talk about that a little bit more, we could see that the PLA produces 0.834 kilowatt hours, kilograms per the PLA, but the release is 1.57 kilograms of CO2. So you could see that the release of the emissions is greater than the production generated from the electricity. And this leads us into the next material of the bamboo, which is similar, also produces 0.833 kilowatt hours of kilograms per bamboo and releases 1.83 kilograms of CO2. So you could see that the release of emissions is greater than the production generated for electricity. So for this LCA for bamboo, it starts off with the bamboo plantation. We have the harvesting and the air drying of the bamboo, the cutting and the stripping, the BBAP treatment and the drying, the gluing and the pressing. That's the main part to focus on. And then along with the CNC mining and the gluing again, this assembles a laptop completely, and then this leads into the use from the consumer and then the disassembly. So the disassembly leads either to the landfill, the recycle, or again the electric production, as talked about before, with the more emissions being produced than the actual production of the recycled electricity from this product. So now moving on to this next topic of the life cycle impact analysis. So the impact assessment was performed using the U.S. Environmental Protection Agency tool, and this was for the reduction and the assessment of chemical and other environmental impacts. So in the U.S. alone, electronic waste was comprised of 1.4% of the municipal solid waste stream in 2012. So that's only 29.2% of the electronics in the US were collected for recycling. So I just want to talk about the functional unit of this laptop. So the functional unit served is a single laptop enclosure with a 43.9 centimeter, which is equivalent to 17.3 inches, and its useful life is 3 years. So now we can compare the useful life and the function to the percent of the 29.2% of the electronics that are only recycled in the US. That's a low number, and that's why emissions is pretty high, and the researchers are trying to get a better handle of recycling this material. So on the next few slides, I'm going to evaluate the breakdown of the results of the materials for the aluminum, the PC ABS, the PLA, and then, of course, the bamboo. So to speak of this study, there was a lot of different scenarios that were considered throughout this article, and the findings from these analyzed were used to identify the best option for the inclusion in comparison of the concurrent material analysis provided. So this graph displays a normalized impact score for the aluminum laptop enclosure that was prepared using the below value items, which was the DC, which stands for the die casting, the CNC mining, the CTG, which is cradle to grave, and then the R for recycle. So the die casting appears to be reducing all impacts by approximately 90%. So given in this article, the recycled metals are known to have reduced impacts when compared to the primary metals for impacts like energy use, water generation, and then aluminum must be recycled to support this option. And the scenario for the die-cast aluminum laptop enclosure with the EOL, which is the end of life recycling, was selected for the final material analysis to be evaluated. Now moving on to the next material of PCABS. There was a total of 24 life cycle scenarios that were run for this PCABS, accounting for the flame retardant selection of the BPB or the TPP. And this was recycled materials content of the 0%, the 20%, the 40%, 60%, and 100%, and the end-of-life processing such as the recycle and the landfill. And these are represented on the y-axis. As you could see to the graph to the right, there was two options for a flame retardant. There was the PCABS TPP and then the PCABS BDP. So the PCABS TPP had a yield impact that was 2% lower on average than the PCABS BDP, and this was part of the 6 impact categories, with the larger impact reductions of the 17%, the 16%, the 20%, and then the 8% for the carcinogenic respiratory effects, ecotoxicity, the fossil fuel depletion, and then for the current study, the potential toxicity of the various flame retardants is not reflected in the human and the ecological health categories. And this is due to mainly the lack of the data to support the deviation of occurrent characteristics of those factors. And then to summarize this analysis, the average global warming potential during the manufacturing obtained in this study was compared with the value reported by Boyd, which showed the inclusive of the flame retardant and the filler substantially increased the global warming potential. And that increased from 5.7 kilograms of CO2 per laptop to 23.4 kilograms of CO2 per laptop. And this was based on the analysis that was provided in this study. And also, I want to conclude that the PCABS TPP was the material that was selected to move forward in the study of the concurrent material analysis. So this next material is the polylactic acid, also known as the PLA. Again, on the right, there's a graphical visualization of what's going on in these results for this material. So to explain it, the impacts of the landfilling are only 3% greater on average for 8 of the 10 impact scores. Generation of the electricity for end of life increases global warming due to the combustion of the emissions created. And based on these results, the generation of electricity on site at the waste electronics producing was selected as the option for the concurrent material analysis. So the generation of electricity was selected to move forward and analyze. However, we do see that the global warming potential is increased compared with the BOYD, which demonstrates an increase from the 1.7 kilograms to the 6.8 kilograms of CO2 per laptop due to the inclusive of the flame retardant and the fillers. So we can see that these materials are increasing global warming. So when I go to the conclusion, it's important to note that all of these materials has been increasing more than decreasing the emissions. So now moving on to our last material, we're going to analyze bamboo. So there are 3 end-of-life options that were provided in this study, and those included the electricity from bamboo and plastic recycling. It included landfill bamboo and plastic recycling, as well as landfilling for both of those materials. So the analysis identified the same trends as when comparing the PCABS option because of the small mass of the bamboo in the laptop enclosure. However, the reduction in the impacts achieved through the recycling is offset by the increased energy impacts associated with processing the bamboo using the CNC machinery. The bamboo PC ABS TPP laptop with the 40% PCR bamboo disposal for energy generation and then plastic recycling was selected for the further comparison. So again, the disposal of the energy generated and the plastic recycling was moving forward the study. So bamboo PLA DOPO is a scenario that included electricity generated from the entire enclosure, electricity from the bamboo and the landfilling PLA, and then also the landfilling the entire enclosure. So the difference between those impact scores for the 3 options that I just explained is less than 0.1% for 8 of the 10 impact categories, with the emissions from the electricity generation increasing global warming potential by 4%. So as I explained in above slides, of bamboo generating less electricity than it was producing emissions, we could see that here the value is 4% higher for global warming given this material. So the use of the bioplastic in place of the fossil plastic leads to significant reduction of 92% and 29% of the ozone depletion and the global warming potential. So based on the impact results for this bamboo PLA DOPO enclosure with the energy generated, that was the one that was selected for the concurrent material analysis. So now to summarize all of those materials into one graph, we're going to go on to the data interpretation. So this graph shows the final results of all the raw materials. So we could see that bamboo has the largest impact, followed by aluminum, and then the plastics with no meaningful distinction between the plastics. However, when evaluating the human health of the impacts from the carcinogens, it has the largest uncertainties of all impacts, with only a general impact trend of the aluminum, the bamboo, and then the plastics. The range of uncertainty for ecotoxic only supports an interpretation that bamboo and aluminum have larger impacts than plastics. So the bamboo and the aluminum did not serve as well as the plastics did for this case study. So to summarize what we've learned, this study was used to better understand how to promote environmental sustainability for consumer electronics via materials selected from the laptop enclosures, as explained above, those materials of the aluminum versus the PC, ABS, the PLA, and then the bamboo. And then the majority of the carbon emissions for the laptops can be attributed to their manufacturer. So that's where it starts. It starts with the manufacturer where all of the emissions are released. So this is most likely the reason behind the companies turning to the bio-based materials during the product design, which means to reduce the carbon footprint of production is their main goal. And then the comparison of material is a fossil plastic blend of PABS. And then the alternative materials include the polylactic acid, the bamboo, the aluminum, and then the various combinations of those materials known to be like currently used or being considered for the use in the laptops. So this study identified the different materials that can potentially be used in the laptop production. So there is a PCR, which is the post-consumer recycled content of 32% for the aluminum. Therefore, currently the recyclable aluminum is not a better option than plastic, and that could be concluded from the study that plastic was better than the aluminum and the bamboo alternatives. If this is represented for all the material enclosures, material use can be improved by increasing recycled content in the final product and offsetting the need for primary metal extraction. So again, the main goal that the researchers wanted to get out of this was to recycle more, to use products that are going to decrease global warming, decrease the emissions produced from the product of the laptops. And due to the high demand from the consumers, this is their main goal, is to find a way to efficiently reduce those emissions. So side note, for fossil plastics, the material performance increased with increased postal consumer recycled content. That's how they evaluated that plastic was better. They used those graphs to show that plastic was better versus the aluminum and versus the bamboo that did not produce what it needed to produce in order for it to be sustainable. And then a material option that is environmentally comparable to the fossil plastics containing the large PCRs based on the hypothetical life cycle modeled in this study is the bio-based plastic. So the PLA DOPO. So as I explained before, yes, the plastic was the option to go with. So the main takeaway from this article is the life cycle assessment demonstrated that plastics compared to the other materials are currently one of the performing materials in terms of having the lowest potential environmental impact for a greater number of impact categories based on the product life cycle models displayed in this study. So going back to those graphs, we could see that the plastic did not have as great of an impact on the emissions and global warming as the bamboo and aluminum did. So therefore, to conclude this presentation, leave off with plastics being the best option for the laptop enclosure. Thank you guys for listening.